So this is lab 7, flexure and strain. So this lab introduced a new test method to measure strain. Previously we've used ANSYS, done it physically in lab, and now we're looking at strain related voltages using a strain gauge and flexure tests, which is beam bending. A little background on this lab. So for the tensile lab, which was a previous lab we did, we were able to measure tensile loads directly acting on test specimens, which we measured by elongating the sample directly and testing the machine crosshead movement. But for this lab, we looked more at complex loading, bending, and comparing these precise measurements with a strain gauge against crosshead displacement. And then finally, we compared the bending stiffness calculated using measurements and the company beam theory. And then so the overall hypothesis we were answering, or our objective, was using equations to compare experimental beam bending behavior to theoretical beam bending behavior. And to visualize this, we did it graphically with a stress versus strain curve, and then a load versus displacement curve, and then we compared the Young's modulus of the two graphs. So the process was conducted on a rectangular piece of clear plastic, and then the primary equipment we used was a strain gauge, multimeter, the 3-point bend fixture, plastic, and then a semicircle. And the controlled variable was force. And then for this lab, the procedure was we sanded down and measured a clear piece of plastic, and then we applied adhesive and then laid the strain gauge down on the specimen. And then we hooked the strain gauge up to the multimeter and read the voltage, which got us our resting voltage value. And then we bent the specimen around a semicircle and read the voltage, which was our strain voltage. We did that 3 times and found the average. And then we used the 3-point bend fixture to bend the specimen, and then with the gauge facing down, and recorded displacement, force, and then the voltage. And one thing we made sure to do was keep the force under 9 newtons.
We took our force and displacement through a video recording both the strain gauge or the displacement gauge and the what's it and the force dial. And from that we took 20 points, which was relatively easy, and we plotted them out here. And as we found our Poisson's ratio to be about 0.0375. Or not Poisson's ratio, sorry. Stress strain. Oh, sorry. Can we go back? Um, our stress versus strain, as we found through the equation given in the lab report, and from that we gathered that our roughly our Poisson's ratio is about zero point 0.6, and it is a linear graph. This is where we run into a little bit of issue, as the guide and the instructions were a little bit unclear to us, and so we did not know exactly how to proceed with trying to find the what this graph wanted. So we assumed it was a displacement versus our MZ, or I think M2 as it was on the whiteboard, and we just kind of went with that because it to us it was not very clear, and this is a major problem with our data collection, as we did not know, therefore our data might be completely inaccurate.
Yeah, so building off of that, with the Young's modulus, the first one that we got off that graph earlier from the stress and strain is that 0.589 gigapascals. And then the second one was from the force, or the force versus displacement graph. And then the reference value that we got was the 0.43 gigapascals. That was the one that was closest to the ones that we have here. And it looks like it was a plastic named polycaprolactone. That's just what we're assuming it is, since we don't actually know what the plastic is. And through these Young moduluses, our percent errors are quite high, 36.9% and 91.3%. And we'll explain more about that in the next slide. So there was some complications surrounding the adhesive process, where the glue didn't fully stick, and when we were bending, we didn't realize until after. And so I think the numbers are probably skewed, which is why the percent errors are so high. And then also, as we said earlier, there was a lot of we weren't really sure how to graph the deformed bean graph, so that also was probably why that our data is a little bit off.
So in the future, I'd say we look more to improve the strain gauge application process and make sure we did that more diligently to improve our overall results. And one thing our group concluded that we were intrigued in was exploring values closer to the specimen's fracturing point. We think this would have been interesting as we only observed one part of the stress versus strain graph, and we were interested to see how the plastic and the voltage would have changed if we had reached a fracturing point. But we understand that through the strain gauge itself, it probably could not withstand said fracturing, but we were still intrigued with what the voltage may look like at that point.
And then just to conclude everything, we have the 0.589 gigapascals and the 0.0375 gigapascals for the young moduluses with the 36.9% error and the 91.3. Obviously the experimental and the theoretical values were pretty off, but that was probably a lot due to the application process just skewing everything. So, we tried our best.
As
And
far
there are
as
some,
questions, oh, I'm sorry. As far as questions and answers go, the most, the dimensions most critical to the stiffness value was our gauge length and width, and the shape of the curve of like the shape of the curve does not match the form beam observed on test at all, and that is because of earlier discussed complications with the third graph and how we tried our best, but we did not know what the experiment wanted out of us, and as such, we did not know how to proceed forward, and so we didn't graph it properly.
this is the reference we used for the piece of plastic, and overall, we feel this lab was successful in demonstrating how voltage plays an effect in the Young's modulus of a particular specimen. And it was a new way to gauge strain, which was interesting in comparison to the previous methods we've used.